So the first thing to know about electron orbitals, let's just take hydrogen for example. When we draw this circular orbit around the hydrogen atom, we aren't actually saying that the electron just spins in a circle. What we're saying is that in an experiment, we actually can determine that there's a high probability of finding the electron close to the nucleus. And as you go further out, there's less of a probability, but there is still a chance to find it out there. And so we say, let's draw a gradient, is what it's called, around the probability density so that we enclose 90% of the probability, or there's a 90% chance of finding it. And what we find is that when we draw this, this actually creates a ring. And so that's what we call our orbital. And for example, this is the 1s orbital. To understand what these mean, we go to the periodic table. So on the periodic table, we have to consider helium over here. I know it's not, but just consider it over here. These first two columns we call S. These 6 columns we call P. These 10 in the transition metals we call D. We consider the uranic elements with the F orbital, but in a beginner chem course, you're not going to do anything down here, so it doesn't matter. S, P, and D are the main orbitals. So what are orbitals? Well, we have our energy levels. These are called the energy shells, and they are the rows, and they go on to infinity, and they actually tie back into the Schrodinger's equation, but you don't have to worry about that for now. As you go up in energy levels, you start introducing more and more subshells, and inside these subshells are the orbitals. The orbitals look something like this. You have a circle for S. For P, you have something like this. And then for D, it gets a little bit more complicated. The first one's really cool because it looks something like this, right? But then you get cloverleafs. They are hard to draw. And then something like this. Oh, I didn't do that right. Oh man, I gotta redo that. Okay, let's try that again. So something like this. Yeah, that's not much better. Anyways, something like that. So when electrons actually fill these orbitals, this is how they do it. Your first electron goes spin up, and your second electron goes spin down. The electrons aren't actually spinning. It's kind of like a magnet. We say one side is positive, one side's negative, one side's north, one side's south. But there's no intrinsic value of north. We just say it points towards the North Pole. Electrons are the same way. They act in opposite ways when subjected to electric and magnetic fields depending on their spin. We had no better word for it, so we just called it spin. So when someone says a spin up or spin down electron, just know that they are the same thing but opposite, just like north and south, or positive and negative. So I think it's Aufbau's rule that says there can only be a spin up and a spin down electron per orbital. And then we have Hund's rule, which says that given multiple orbitals, electrons will fill one in each first, and then start creating pairs. So this is Aufbau, this is Hund. So the question asks, in the d orbital for an energy level greater than or equal to 2, how many electrons can fit? Well, I don't know why they would say greater than or equal to 2, because in the periodic table, there are period 2 elements with no d orbital, which doesn't make much sense. So I don't know what it should have been 3. Yeah. Anyways, so in our d orbitals, this is kind of hard to visualize, but along this entire pathing, we're going to have a spin up and a spin down. And we're going to have a spin up and we're going to have a spin down. And we're going to have 2 electrons in each orbital. And they're going to be in the similar spots, but they're going to be opposite to each other. But I'm not entirely sure what opposite means on a cloverleaf, so leave it up to your imagination. Obviously, this is simple. We have 2 electrons per orbital. That's just going to be 10 electrons. The easiest way to remember this is there are 10 elements that span this area. For the S, we only have 2 elements. For P, we only have 6. So, if you're ever confused on how many fit, just remember the periodic table. I'm sure you have one in your class, so it should help during tests. I used to use it a lot. And of course, P works the same way. We'll have a spin up, we'll have a spin down, we'll have a spin up, we'll have a spin down. And then, of course, it continues on. I think that's it.